Hello everyone. So now we will be working on script 7 and example 7, which is pretty much similar to what we had before for example 6, which was for static loading. Now for script 7, we will be working on dynamic loading. And the intention here is to show you a Python script that can extract forces in the piles, but now we have the complexity of applying an earthquake at the base of the model. You can see here, apply earthquake loading, and using the Python script to extract the forces at each time step within the time history that we applied here. Keep in mind that if we have a time history, it means that we will have a significant number of points to interrogate. And as such, if you have a model where you have lots of piles, it may be practically almost impossible to extract all the forces in all the piles, because this will take a humongous amount of time to do that, unlike the case of static loading. So what I have opted here is basically to ask the Python script to go through all the piles and then identify the piles that are the most critical. How? Let us see this. So if I come here and if I have a concrete pile, for example, like I hinted in the previous example, so we would have the bending moment, normal force, failure envelope, which is this thing here that you get from the structural engineer. This is something you need to familiarize yourself with. So basically, if I have this failure envelope, all I need to do is to identify the cases with the most critical combination. For example, as I'm saying here, this would be the cases to consider. So I would determine the resultant moment, MR. Why I'm saying resultant here? Because if you recall, so in PLAXIS, we have two orthogonal axes that give me bending moment M2 and M3. So MR is the resultant moment, which is simply the square root of M2 square plus M3 square. So I can identify the pile within the pile group, within the time history, within the elevation or the length of each pile, to identify the case with the maximum MR. If I succeed in doing this, I should be able to get the corresponding axial force. For example, if it happens that pile, say, number 4, at time, say, 7 seconds from the time history, at elevation, say, 8 meter, has given me the maximum bending moment resultant, MR, within all other piles, for all other time steps, for all other Z elevations along the piles. So then I would say, okay, I got you. What is the corresponding N? So I will get the corresponding N at this particular pile, time step, and the elevation, and then I locate a point here. If the point is within this failure envelope, I know that structurally I will be safe. It's not your decision, obviously, to say it is safe or not as a geotechnical engineer, but you should be able to communicate these results with the structural engineer for him or her to evaluate and come up with a decision. So this is the first combination, the maximum MR and the corresponding N. And I would repeat the same case, but now the maximum N intention, because if I'm located within this zone here, below the dashed line, so most probably the failure will be intention. So I can identify again the pile, time step, the elevation Z, where I have the maximum N intention, and I get the corresponding resultant moment. Look, when the structural engineer works, he wouldn't know what is M2 or what is M3 in PLAXIS. What he would know is what is MR. And again, I would repeat the case. Perhaps this needs to be in red also. So I would repeat the same for the case of the maximum, for the maximum N in compression, or choose be minimum N in this case, if we follow the sign convention, and I get the corresponding MR. So these are the three basically combinations that I need to check the structural capacity of the pipe from the MN perspective. But I also need to check the shear force. So there is a third case. It's not related to this in particular, but it will be needed for structural check of shear. So I will get the maximum resultant shear, that's a Q resultant, QR, and I will get the corresponding N and the corresponding MR. Now, since we know this, so we can then go back to this problem and say, okay, my intention is now to only identify those piles, and then I can extract the forces only in these piles. So this means that I have here 4 cases, 1, 2, 3, 4. All I need is to identify these 4 cases, and then I can continue. If I'm interested in a particular pile, then perhaps a different Python script would be needed. But I opted here for efficiency. You will see in a minute how long this, the case we are studying, will take to run the model and implement the Python script. So let us see the PLAXIS model. So the PLAXIS model that we have is coming here. So hopefully this will continue without issues. So this is my model. It's exactly the same as a static model. This is where we had applied the static load. However, let's hide this. So this is the case. However, I'm now applying an earthquake loading similar to the dynamic cases that we studied in this course so far. Again, this course is not about how to apply dynamic loading, but I'm explaining the Python scripts. And on the side, I give you sufficient background to understand. So here I'm applying earthquake, and the way we did this is, if you remember, so we would have 1, 2 this side, and also that side, and the base. In this model, I added these 2 other sides, because in the end, the earthquake loading is gonna come parallel to the X direction. So, and at the base of the model, I have applied a load here in the form of, if you see, surface displacement. So I have this done already, and then I generated the mesh here. As you can see, I did not select any points for curves or anything, because here all I'm interested in is in these piles and the critical combinations. Then I went to staged construction, and then statically I applied here a vertical load, which is 100 kilopascal pressure. And while this 100 kPa is still there, so I came to the base of the model. Here is the base of the model, and then I activated the displacement. Well, this one here will be taken over anyway, whether you check this one or not. It's a good idea not to check it, but you can show this, but it's not going to make any difference in PLAXIS. So just for the sake of clarity, we don't have to show this. Then you will apply a surface displacement here, which is the form of time history of the earthquake. I'm repeating what I explained before, just for completeness and clarity. If we go edit to this multiplier, edit. So basically this is the displacement. Like I said before, you are free to either apply time history in terms of acceleration or displacement or even velocity. I opted here to use displacement because this will be more efficient in terms of the execution time. Make sure that this is displacement and this is just the multiplier, which you can change the name or do whatever it is. So this is the case here, and it is essential. It is essential here. This is a prescribed X, and it has to take 0.5. This is requirement by PLAXIS to get the time history applied correctly and the corresponding response spectrum within the soil model and at the ground surface correctly. So this is just more of the way it's calculating, because you will have bedrock below that surface here. Again, this is outside the scope. So I.5, so what PLAXIS does is it goes, again, so it goes at each time here, I have 40 seconds, so at each time step here, so it work out the dynamic multiplier, and then it multiplied by this value here, which happens to be 0.5, and it has to be 0.5, and then apply this as an explicit time integration approach. So, and then I also say for the displacement y, I don't expect a movement perpendicular to the page along the y-axis. So I said this is prescribed and it is 0. And for the z, I said it's a free, so that the points can move vertically at will. So this is how we calculate, or this is how we apply the earthquake loading. Like I said, normally and more conventionally, people apply the accelerogram, like in terms of the acceleration versus time, as a time history thing. So let us see what we are applying here. So double click on this, and this is 30 seconds, which represents the duration of the earthquake. However, again, if I go back to the displacement multiplier, the time history, I have 40 seconds, but I opted to save a bit of time. So I said 30 seconds should be enough to inflict the piles with the maximum forces. So double click again on this. So this is 30 seconds, and you know now my style. I am using here 400 points only, again, for efficiency of the calculations. And when it comes to use default iteration parameters, so you don't want to check this, don't leave it to PLAXIS, but make sure that you have enough points for your analysis to be accurate. Okay, so if you choose here the maximum steps, if you choose here like 10, for example, so rest assured that your results will be incorrect. So there is a trade-off between how many points I can choose to be pragmatic and at the same time to be reasonably accurate. So I opted here for 400 points. What does this 400 points mean? I'll explain to you in a second. And then I say the number of sub-steps is 1. So this means that all I'm applying is 400. So I'll explain to you what is meant by that. And I zeroed the displacement here. It's up to you to zero it or not, but it's a good idea to zero it so that any displacement you get would be applicable essentially to the case of the dynamic loading. So I would close this. Now let me go back to this displacement edit. So basically I have here how many points all in all? It's 400. This is my habit. My style is to choose here sufficient number of points, and then I use the same number of points in the calculations here. So 400, as you can see here. So this means that you have 400 points making up all these points and curve that you see on the screen. Okay, so this means that I have reasonably enough coverage because I am tracing all of this. So if you don't do this, I'll just show you something quickly. Hopefully this can come as, okay, that's not the one. Okay, if I go to PLAXIS, let me show you this in PLAXIS. File, open, hopefully I can see it clearly in PLAXIS here with you. So do I have time history here? So let us see all files. So I have here the time history. You can see displacement time history here. So this is, open this, and we will go next space. So we have it, finish. So this what I have. Okay, I have 400 points here. So I will draw this. Pay attention to this, because this can be very critical, and it can make the difference between the accurate and the no accurate results. So I'll just make this. So what happens here is, okay, now if we have used 400 points, it means that when PLAXIS does the integration, explicit time integration, so it basically follows each point of those to cover the 30-second or the 40-second we're applying. Now imagine, because I'm using 400 steps, that's 400 steps. So 400 steps means that PLAXIS will follow this more or less closely. Now, if I use, for whatever sake, for only 20 points, so this is what will PLAXIS do. Okay, pay attention, and I will draw here a circle or maybe a square to represent the points. I'm exaggerating here. So PLAXIS will start with this point, and then because it's a 20, PLAXIS is gonna spread out this 20. So you may have another point here, okay, another point here, another point here, okay. You get the message. So point here, point, till I consume the 40 and the 20 steps, okay. So pay attention to this. Okay. Assume that this would be the 20. So this is how PLAXIS see this as a loading regime. So I would go to line here. So PLAXIS will say, okay, I am connecting this to that. Okay, we will give it maybe different color. So give it black, and then I will see the next one. So this is the next one. You see now how I started to deviate from my loading regime. This one here, and then, sorry, copy, paste, you get the message. So, and this is now the regime that we are applying. So, a new one here, like that, and here, I'll just show you in a second what I'm arriving at. Control P, you get it, you get the message by now. So, now let me just move this out. You see now the shape that PLAXIS is considering, because I give it a small number of steps to do the analysis. Now compare this loading shape now. Still, what PLAXIS sees. PLAXIS will not see this during the calculations, but PLAXIS will see this, which has deviated dramatically from this detailed shape. And as such, don't expect that you will get correct results from this. So what is the alternative? Like I said, there is a trade-off because the execution time can be significant. Okay, so all good now that we understand what's happening in the background. And if this is earthquake loading, as you know now, we have to go through model conditions and to go to dynamics and make the far end in the x direction. Minimum x is free field. Also, the maximum x would be free field. So which is that side here. This is the maximum x. This side here is the minimum x. And we'll make the minimum and maximum y none, and then we'll make the z minimum compliant base. Compliant means that it's not going to be a fixed boundary anymore. Okay, so and I did not spend any time talking about the soil. That's another thing. But again, this is a hardening soil small with also additional Rayleigh damping that I use here. I'm not going to go into details here. Okay, so I did the analysis. How long this analysis took? From memory, it was not that bad. This was about, say, 50 minutes. It's not that bad. But if your model is bigger, so you expect days, depending on how powerful your machine is. Now, let us go to the calculation results just to show you what I have obtained. So now what I have is, you see that always PLAXIS gives you something on the edges here. It's not a big deal because this is area of interest for us. So switch between phases. So I press this one to be able to see the time steps. May take a bit of time, so we wait until it flicks. Yes, and you see now I have all these time steps. Okay, and this include actually step 0. Step 0 is when the initial phase. Step 3, this is the end of phase 1, and step 7, this is the end of phase 2, and then from step 8 to the last number of steps, which is 407 here. So I would have the time steps for the earthquake analysis. Okay, and if you choose structures here, if I'm interested to see, so this is these are the 6 piles that I have, the same 6 piles that we had from the static. So let's open just one of those. So this is the axial force, for example. You can see this axial force, it changes both along the pile length and also with each time step. Look at this here. So it's just giving you the maximum values here, but just look at the values. For example, the footing here is, the end bearing is 203.5 kilonewton. Let us see if we pick another time step. So it's now has changed a bit, okay? And every time you go to a new time step, so the distribution, the maximum values will change. Hopefully it will change now. Change it, as you can see, and also the end bearing change. So it's quite challenging to interrogate these results manually, and this is why we have this Python script. Okay, so I need now to see how we can run the Python script. So from here, if you remember, I already have it. So from here you go expert, Python, editor, and then you say start server, and this will start the server for you. Okay, I have done this because the time you will see now in a second is significant. Okay, so when you start the server and then you say close, it will open for you this thing here. I already have analyzed this model. I'll explain to you in a second. So this is a script, a Python script that you should have access to as part of this course. And you have here clear instructions. All these are comments. So basically what it does, like I said here, it goes through all the piles, all the time steps to identify these 4 conditions. And once it does, So it produces or print out the forces in this pile that has been identified. So I should have a case of four identified piles. Like I said again, I'm repeating myself, I did not opt in this to get the forces in all the piles in Excel because this can take very long time. The trouble is, you will see it in a second, the trouble is PLAXIS goes through this sequentially. So PLAXIS has to step through each pile at each elevation, at each time step, and show as a scrolling down presentation, show all of this here within this window, and the Python script has to read it sequentially. And this is why this is a bottleneck. It is not something that we can control. However, what we can control is to have this as efficient as possible, which we have in this thing here. So I did the analysis, and I will run one with you again. I did the analysis, and this what you will get in the console. Okay, so what is that? First, it says the phases available. So it scans all the phases. I have 0, 1, 2, 3 phases. All in all, 4 phases. 0, 1, 2, 3, as you can see. And also it says enter the phase number to analyze. So this is a question for the user. It will ask you, as we'll see in a second also when I run it again for your sake, it says, which phase are you interested in? So I'm interested in phase 3. So you just input phase 3, and then it will start working. Okay, so it scans, you can see it says scanning pile 1 of 6, 2 of 6, 3 of 6, and so on. And then it managed to identify these 4 critical cases. Again, the 4 critical cases are those. I need the case of maximum MR with the corresponding normal force, and then the maximum inattention, if any, with the corresponding MR, and so on for the maximum compression or minimum N in this case, and the corresponding MR, along with the case of maximum resultant and obviously the corresponding. When I say the corresponding, it means at the same time step, at the same elevation where the maximum value basically occurs. So, and then it even gives you some values. So pile 1 is the pile with the maximum MR, and for pile 2 is the one with the maximum QR, pile 3 is the pile with maximum N, and pile 1 is the pile with the maximum minimum N. And it opens, it gives you a file name that changes every time. It changes every time you run the script based on this formula here. So let us see the results that we have. So this is a result. Okay, let's first tell you how long this has taken. So the execution completed in 665 seconds, which is about 8 hours, believe it or not. So this case is an example of how this is what we have, and just confirm, divide this by 3600, maybe not, maybe less. I think it is less than, divided by 3600 to convert seconds to hours. So actually it's close to 4 hours. My bad. So this has taken 3.8 hours to run. I have other cases for real projects where this has taken 30 hours to run. So it can be quite painful, but it's quite rewarding because you're going to remove lots of issues. I did not explain to you why it is useful to do time history analysis. You can refer to my course on Udemy about advanced earthquake analysis for pile foundations. So there is a wealth of information there, including how to do site response analysis, etc. So But let us see how this is recorded in the Excel files. So this is an Excel file. I think this is data modified. I think this is the one. So let us open this. Hopefully this is the one. This is not the one. Okay, searching for this file. So we have this output file. That's the file name here is again dynamic. So every time you run the script, it will give you a new file name. So if you double click on that, it will show you the nature of the results that we have. With this here, for example, this is extreme summary. Extreme summary would be basically an image of these results here. So if I go back to this, so it's telling me that for the case of maximum MR, this is a value. It happens with pile 1 at this depth, which is almost to 0 here. Time step is 98, and the corresponding Q resultant is 32, and obviously MR is 57, and the corresponding axial force is this value in compression, and the coordinate of horizontal coordinates of this file is 26 and 27. And the same for maximum QR, maximum M. Now, if this pile 1, has the maximum MR, so this is the full results for the maximum MR. So this is for pile 1 by definition, and this is the data along the depth for all points along the pile length. Let us try to draw any of those and compare it with what we've got. So I'll just draw something here, something like that, and then adjust it. Okay, because I'm interested in the I want the Z. So let us plot M3 versus depth. Okay, so this is what we got, and basically we can just make something like that, and we add line. Say this would be the distribution of what happened here. So this would be the distribution of the bending moment. The maximum value that I have here is 57, as you can see, at elevation 0, which is consistent. Let's compare this with what we got, just as a check the results are consistent with the output. So if this is my output, I press here to check the results, and then I say this is the embedded beam view, and the pile in question, it has X and Y equals 26 and 27. So we can go back to this. Hopefully this would upload. It's not gonna crash on me. So this will upload the various piles. Okay, while this is happening, I don't know why it's here. Okay. Yeah, so if you would like to check the coordinates, in case you don't know the pile number, so if you check these coordinates here, so it's telling me that this pile is 26, 27, so I will double click basically on that pile. I'm double clicking on that pile here so that I can isolate it, and then compare the results from this manual inspection with the results in Excel from the Python script. So I'm waiting for this now to load, and we will be able to compare it. Takes a bit of time. Okay, so this is that pile, so forces, let's say M3. So, and I need, if you remember, it's telling me here that the maximum is happening at time step 98. So we have to follow this 98. So I would go here and go back to 98. So this is 98. So the 98, basically, that's 57.46. That's correct. What did I draw here? I draw here M3. That's correct. What I'm comparing here is M3. That's correct. And let us see the shape overall. The shape is correct overall. And you can see the corresponding value is 461. So let's check at 0.0. So if I go here and force N and at this value here at the top, I can do this and can come here to see it. It's 461 as we said. So, but let's go back to M3. So the meaning of these results is that this pile has the maximum resultant moment among all piles and among all time steps. This step 98, and this is defined as z equal 0. So this means that although I'm seeing here M3, but if I see any other time step, the value at the top, you will expect to be lower. So let us see here. It's loading, it's 34, it's lower, and so on and so forth. So this makes me happy that the script is working properly as expected. But I will show you now, because this took shy of 4 hours, I'll show you now if we were to run this manually ourselves. So I'll just close, erase all of this, and I would review what's needed here. So it's telling me that the local host port should be 10,001, and we'll check here so that it doesn't give me error. If it gives error, this could be one reason. So this is 1001. I'm a happy man. And also this is so it will ask me about the phase number, and I know from the analysis I'm interested in phase 3, so I will feed it with this phase 3. So let us run the script. F5, pressing F5 now, or go to tools and then go F5. So the script is running now, and I will spend like the first couple of minutes just to make sure that, so it scanned phase 1, phase 2, phase 3, and it say enter the phase number to analyze. I'm interested in phase 3. You can see now it will start saying I'm scanning pile 1 of 6. I'd like to show you something interesting which proves where the bottleneck is. If you see this here, can you see? So it is scrolling here, as you can see. Unfortunately, this has to be done. It's a sequential process. But one way to accelerate it, you can remove the geometry. Don't show the geometry. This may make it a bit faster. Make it a bit faster. And if you can remove as much as possible, so view, for example, and I can hide the model explorer, and I can even hide the title, so that none of this needs to, so this would make the script a bit faster. But as you can see here, the output file is scrolling, actually scanning sequentially all these values. So this actually explains why I advise that we just focus on the maximum or the extreme forces and the piles identified with these extreme forces and the corresponding other parameters. So this will run for 4 hours, like I said, but well, if you need to do it, then you will do it definitely. Now the configurations of my machine, if this would help you at all, to basically work out how long this would take on your machine. So a model like this with 6 files took 3.8 hours. So I will now go to the computer and I click for you to see the properties. So the properties here, as you can see, the processor is 2.5 gigahertz speed, and I have 32 gigabyte RAM. And with this, it took me 3.8 hours. I experimented with powerful, more stronger machine, and really you can reduce the processing time significantly if you have higher specifications. I tried with for example 3.5 gigahertz and 132 gigabyte RAM, and the speed was 5 times faster. So it is still practical from project point of view. Anyway, hope you have enjoyed this video, and I will see you in the next one.